Well, friends, at school we've all learned something called Euclidean geometry. More specifically, in this case, I'm going to talk about coordinate geometry. The main thing about it is that it maps things in a two-dimensional space with a y-axis and an x-axis. Take, for example, this point. It has an x-coordinate of -3 and a y-coordinate of 5. Great. We can see its position on this two-dimensional plane. However, it's not very useful for mapping out things in motion, for example. Let's take this point. You could argue that you could draw a series of points to show how its position changes in this two-dimensional world. However, speed isn't like that. Speed is distance divided by time. That means it's distance per time. That means you have to say it in something like kilometers per hour or meters per second. We're giving the kilometers and the meters, the distance here, but we're not giving the time, the seconds, the minutes, the hours. Speed, motion, velocity, they all have to be described in time. That's why nonlinear geometry basically states that in coordinate geometry, it's better to give an extra axis for time. And this goes on to special relativity. Special relativity really took this idea of adding a time axis to create many things that were very useful to our daily understanding of life. Now, before I get into special relativity and the next part of it, general relativity, and today's string theory, I'm going to go on to what the main points of nonlinear geometry actually are. First of all, Euclidean geometry. You know that basically, Euclidean geometry describes things on flat surfaces. That means that in Euclidean geometry, lines are always parallel. No, sorry, lines are not always parallel. Parallel lines never meet, and triangles, their angles always add up to 180 degrees. Now, in nonlinear geometry, there are two main parts of it. There are others, but these are the two that we're going to focus on. Lobachevsky geometry and Riemann geometry. In Lobachevsky geometry, it basically describes things not on a flat surface, but on a concave surface. That means when you draw a triangle here, it means that the angles will always add up to less than 180 degrees. For example, you can draw three 50-degree angles here. They add to 150 degrees. In Riemann geometry, it describes things on a spherical surface. Or, for example, here, I've drawn a sphere, and when you draw a triangle here, the three angles are all 90 degrees. So they total up to 270 degrees, and not 180 degrees. Both Riemann and Lobachevsky continued on the ideas of Euclid. So that's basically what Riemann and Lobachevsky geometry are, and the main points of nonlinear geometry. I'm just going to go into how this can be used in special relativity to further our understanding of our daily life. So as you know, the Sun-Earth position, the Sun-Earth system is roughly in a two-dimensional plane. Any discrepancies are quite immaterial in the whole thing, so it's in a rough two-dimensional plane. Now, if you were to describe this on normal Euclidean geometry, it would probably look something like this, or basically that. However, in special relativity, which adds that extra time axis, it looks something more like this, far more accurately depicting the Earth's motion. In fact, it's special relativity, which was used to help accurately judge the distance from the Earth to the Sun and from the Earth to the Moon. In fact, in special relativity, you can clearly see how the Earth's motion changes over time and how the Sun's position doesn't. Moreover, in special relativity, it uses this to our advantage and describes things with 3 dimensions, but 1 extra time dimension. And it looks for things that are absolute compared to everything else. What I mean by absolute is that, well, in Newtonian mechanics, it states that there are objects that are at rest and that there are objects that are in motion. Some objects are absolute rest. They're in absolute rest. They move compared to nothing else. They don't move compared to everything else. Now, Einstein in special relativity predicted that this was impossible. Objects are always moving with respect to something. You sitting here in this room may think you're stationary, but really, you're orbiting around the sun at an incredible speed. If you're at the center of the sun, well, you're orbiting around the center of the galaxy at an incredible speed. center of the galaxy, you're moving randomly around other galaxies. Even if you were at the darkest void in space, you'd still be tugged slightly here and there, even by tiny micro or nanometers, but you'd still be moving compared to something. And other things would be moving compared to you. Absolute rest is impossible. But there are quantities that are absolute. We'll just talk about some of these quantities that aren't, though. Something like length isn't absolute. Now, you may say, let's just say this is 30 centimeters, and you may say that this is always 30 centimeters no matter which way I measure it. Well, that's kind of true. If you measure it from here or somewhere like that, it will be 30 centimeters, but if you measure it from here, you're only seeing this endpoint here. That means it's only like 1 centimeter. The point is, length can change depending on where you're looking from. However, the true absolute thing here is distance. Let's call this point A and point B. Point A and B, okay. So the distance between these two is always the same no matter where you look. In fact, actually, this needs to be a bit more specific. Distance in terms of something is absolute. Now, this distance may be 2 sticks long, but it could also be 4 dots long. So distance in terms of something has to be absolute. That's one of the key foundations of special relativity. And this can help us create better aircraft launching, better motion for objects such as cars. We can create better vehicles and better accurately measured instruments. Special relativity is essential to understanding our day-to-day world. And in fact, you may not think that the time axis is really necessary in your daily life. Well, you use it all the time. For example, let's say that someone asks you to come to a certain building on an imaginary street, 4th Avenue Street, and you have to go to the 2nd floor. Now, what you do is you move across the horizontal or 2-dimensional plane to your building. Once you get there, you move up the vertical direction to the 2nd floor. Job done, you may think, but no. Say if you go there at 12 a.m. in the morning and you call them up and say, hey, I'm in the exact coordinates in space that you told me to go to, he'd call you an idiot because you're calling him at 12 a.m. You have to specify a time. 4th Avenue Street, 2nd floor of the Capitol building at 3 o'clock in the afternoon. The point is, time has to be specified for things like motion, things like position of objects. In our 3rd-dimensional world, it's essential to map things out in time. In fact, for every dimension. The lowest dimensions in nonlinear geometry that you can go to is a 1-dimensional object. Or a 1-dimensional world, sorry. This is the time axis, and this is the 1 dimension. Now, this means objects move like this, or like this. That means that they move in one direction, but through time at different rates. You always have to use time to map things out. Going back to Riemann geometry and Lobachevsky geometry, they are the foundations of general relativity, one of the greatest theories that any single person has come up with. In general relativity, it's basically founded on the idea that there is this constantly permeating thing called space-time, a combination of space and time, which destroys Newton's law of absolute space and absolute time by combining them together. Imagine a very elastic fabric, like a constantly stretched rubber plate. And now this means that heavy objects will distort it. If you, say, take a paper and you push your hand into it, the paper moves apart. Take a pillow, and if you push your hand into it, it crunches down. Same thing happens with space-time. A heavy object like the Earth pushes down on space-time, creating the hill-like places in space-time that are described by Riemann geometry, and the concave surfaces in space-time that are described by Lobachevsky geometry. This causes light rays, which is actually part more special relativity, to bend across space-time and bend around heavy objects. Again, not because of the heavy objects themselves, but because they're bending around the already curved space-time. So that's special relativity and general relativity. You can already see how a critical role nonlinear geometry plays in these. Now I'll do other videos on special relativity and general relativity. For now, we're just going to go into string theory. String theory, which I'll also do another video on, because it really deserves its own, basically states that from Riemann geometry, that in these axes, you can already figure out that you can add any number of axes. This is just three. This is just three, two spatial dimensions and one temporal dimension. The dimensions that you can move across in the same way that you can move across height, width, and length in our three-dimensional world, are spatial dimensions. Time is considered a temporal dimension. In string theory, time is the temporal dimension, and all the other ones are spatial dimensions. We haven't found out these spatial dimensions yet, but it is possible that we will. In string theory, it states that we can just add on extra axes as long, here's the key point, that they're 90 degrees to all other axes. And these dimensions, it states that there are 10 dimensions, 9 spatial dimensions, and 1 time dimension, as I said. However, Riemann geometry, more specifically in nonlinear geometry, you can predict from the equations that 26 dimensions are possible, which just shows how much of a foundation Riemann geometry is on string theory. Going on to the idea of these so-called extra dimensions, if you've read into quantum string theory, well then you'll know that in string theory, all matter, all particles, are made of these little loops of what's called superstring. Now, superstrings, the key point that string theory states is that they're completely unobservable, because these loops of strings are smaller than something, what we call the Planck distance. The Planck distance is the smallest possible distance that you can measure. Anything smaller than this, you won't be able to measure it. And quantum strings are smaller than the Planck distance. The only way that scientists could possibly measure a quantum string is to somehow unloop it so that it is somehow larger than this Planck distance, and then they can finally observe it. The thing is, these extra dimensions are also probably smaller than the Planck distance, or just larger enough. But the point is, now we can't observe them. Now, I'm just going to talk about a rule in quantum physics that states that an unobserved particle, if it is not being observed, it doesn't exist. Think about that. If you're a quantum particle, and you're in a room with this video, etc., then if no one is observing you, no one's hearing you, smelling you, tasting you, or anything, you don't exist. A particle in this state is a superposition of all possible states that the particle is in, plus it doesn't exist. That means that these dimensions, A, don't exist. But if we somehow observe this thing that doesn't exist, then it suddenly appears into existence along with all of its properties. These ghostly dimensions, as they're called, are highly debated among scientists. So, that's it for string theory. So basically I've summarized that nonlinear geometry is much better than coordinate geometry in mapping things out in the everyday world. It's the foundations of special relativity, essential for mapping out how light works and how the entire universe works, and in general relativity, and moreover, string theory. Nonlinear geometry had its foundations in Riemann geometry and Lobachevsky geometry. It maps things out in a much better way than Euclidean geometry ever can. Thank you.